Everybody, with that, let's get going. Okay, good. So why another database? We get asked this all the time. Why did we need to re-architect from the ground up the entirety of the stack of the database? You know, any database really comprised of three different things. Storage, because ultimately data gets stored to disk. Execution, SQL execution, like, okay, how do queries actually get executed? And then the layer, which is basically most people are familiar with, all developers are, the language, the syntax, right? And so you know, for Cockroach, we have re-architected the bottom two layers. We had to kind of re-architect the top layer, but we're just using basically SQL syntax on top. And what we get is kind of a combination of all the great things that we expect in a relational database around, you know, consistent transactions at scale. But all the positive parts of a NoSQL database where you get this kind of global scale and resilience and all these things. And so ultimately, if you start from the ground up, you know, we can actually take care of a lot of these things. And now, you know, why wasn't this done 10 years ago with NoSQL? I think, you know, I've been in software for a long time. I think we just learn things over time. And this advent of distributed systems and some of these kind of core principles as applied to the database, you know, we've done that. And I think I find it really, really interesting. I think this age that we're in of cloud scale has really started to move us in this direction. How do we use, you know, microservices and how do we reinvent basically the relational database for the cloud? And that's really kind of what distributed SQL is about. And distributed SQL is really truly just an evolution of the database. You know, let's take all the core principles that were built on, including SQL, right? Because that's what people do, right? But let's make it easy to operate and scale. Let's actually take advantage of the elastic scale that the cloud provides and do this in the database itself and automate that, right? The cloud also requires us to be always on and resilient and everywhere. How do we build that into the database, right? All the while, this is going to be relational. So ACID compliant distributed transactions. Transactions in a distributed system are difficult, right? And we're talking about, in Cockroach's case, you know, serializable isolation. So we're guaranteeing data is correct. And then finally, if you're going to be a distributed database, and this comes back to any distributed system, thinking about where data is actually critical to the software itself. And I think, you know, typically when we implement a database, at least me for the last whatever couple dozen years, I guess, you know, I think about that logical model of the data itself. With distributed database, you have to actually start thinking about the physical model. What do I want to survive? Do I want to survive the failure of a region or a node or maybe an entire kind of half of the planet, right? Like, how do I do that, right? And where does the data live in the context of that? Or, you know, where are my users? Is data close to them? So I have low latency access to those things. And so reinventing the database from the ground up allows us to do that. And I'm going to show you how we have actually implemented that underneath the covers, right? So CockroachDB, ultimately, it's a relational database. It just delivers just like you would have a Postgres database underneath. The beauty of it, you just simply keep adding nodes to it and it's going to scale. And it's going to scale both in volume of size of the database, but also in the amount of reads and writes it can do, because every node in Cockroach can actually service a query, right? And we could scale further. We could scale beyond just a single data center into multiple regions. All the while, no matter how you look at this, it's one single logical database. Any node can take a query, and to the end user, it just looks like one database. What's really cool is we can actually do this across multiple different clouds, right? So imagine the regions are just different clouds, right? It's pretty cool and unique to what we are. And now your application just looks like a single logical database connection string, right? We can also survive failure of a node or an entire region. And, you know, this whole concept of RTO and RPO and what does it mean for, you know, active passive systems? This is just truly active, right? And so this allows us to do some really cool things. It also allows us to do some like no downtime, you know, rolling upgrades, which is really, really cool as well. But coming back to one quick thing, before we get to the architecture, actually a really key kind of concept to understand, any node can service a query. It means basically I can query anywhere and it's going to be able to find that data throughout the entire cluster, right? No matter where these things are, we could be in your regions across the entire thing. And this is what allows us to get this like low latency access to this data. But we also allow you to geolocate data so that, you know, when this user Kimball logs in, you know, we typically out of US East, we're going to make sure that that data is going to be tied to that region and we're able to service that query. This is one of those key things about actually addressing latency. It also works for compliance and regulations and whatnot, but that's kind of a key feature. We'll show you how that works underneath the covers next. All right, great. So I'm going to dump into the architecture now. You can write to any node. There was a couple quick questions. You can definitely write to any node. Any node can service a read or a write. That's the trick here. There was another quick one. How are we compared to Cassandra? I will take this very quickly because I want to get into the architecture, but Cassandra is an amazing database. And honestly, I will contend that I think the pandemic would have been horrible without Cassandra. Because like if you think about Netflix, any of these streaming services, these large companies, they use a lot of Cassandra in these places. It is actually implementing transactions is difficult. As from a developer point of view, it's difficult to deal with, right? How do you actually simplify that and actually automate scale and automate transactions and deal with all these different things? And so there's lots of different things. If you go to our website, we provide some more detail in terms of the differences between ourselves and Cassandra. I think it really depends on the workload and the maturity of your development team in terms of what you're actually going to do with that. And a lot of people use both Cassandra and ourselves, CockroachDB. So, okay, great. Real quickly, there was another question. Yes, a recording will definitely be available after this. So, okay, great. Let's actually just jump in. This is my agenda, what I'm going to go through. So I got a lot to cover, and I've got, let's see, 47 minutes. We can do this. We can do this, people. I'm going to talk a little bit fast. I'm going to try to pay attention to questions along the way, but I hope this is available. This is valuable to y'all. So, at the core, I was talking about the layers of a database, and if you think about it, there's storage, there's execution, and then there's language, right? And those are kind of the three logical pieces of a database. Now, at the lowest layer of the database, Cockroach is actually implemented as a monolithic key space. Actually, while we appear to be this relational database to the developer and everybody's using it, under the covers and the way that we've actually implemented this is every table, this is the dogs table, is basically ordered lexicographically by key. So you can imagine the key here is the name of each of these dogs. And so when we actually store data, we're actually using a KV store to actually take care of this underneath the covers. Now, this is a little bit different than a normal database, right? In a normal database, say we had an inventory table, we would just keep appending rows. And the way that that data gets stored is basically like, okay, the next, memory spot, we just throw in that record. And the way we get fast access to this, we actually, create an index, which is a set of pointers that's pointing to a memory location for you to access these things. And that allows us to do things like sorts and scans and all these different things, right? And so that's how the traditional database is kind of implemented underneath. We take a very different approach, and we use kind of KV to do this. Now, when I started working at Cockroach and I understood the KV and how that actually relates up the stack to what we're able to do, that was where things got pretty interesting for me in terms of kind of how this item all comes together. So, like I said, we're ultimately implemented as a KV store, and it allows us to take care of some very, very powerful primitives at that layer. Now, at this layer, we actually had been using RAFT-DB. If you're familiar with that, it's an open source database. It's available. It's pretty cool. And actually recently, we have reworked that layer into something we call Pebble. And Pebble is a new open source project that we've created. You can go check it out, where actually that layer is actually completely written in Go. The entirety of CockroachDB is written in Go. So it allows us to have a little bit more control in terms of some of the things we want to optimize from a performance point of view without having to change RocksDB. So it's kind of taking Rocks and implementing it as Pebble and adding some things that are kind of helping us at that layer, because ultimately performance and some things are really driven at that surface area between the database and the disk itself, right? And so we're doing some really interesting things there, right? And so all tabular data here is just sorted, and all tables have a primary key. Now, the primary key on the table is the trick to actually understanding Cockroach. So right here, this ordered set of keys is just names, but underneath the covers, what we're encoding in the key is the table, what the index is, the key itself, and then typically a column name, right? And then I'll show you how that works. And then the value is basically the value of that column name. And we're basically able to order all these things and do some really cool things. Let me just show you how that works, right? So here's a typical table, right? Here's I'm just creating a table here. This is the dogs table. And here's some entries over on the right-hand side. There's some random, I guess, UUID over there, name, and then weight, right? And so for our case, well, we're going to basically take this ID as the key and start storing all these values. So each row is basically, this is a high level understanding of it. What we do is we break down each row into basically its constituent parts and store those in an ordered way, right? And so what I have now is I know exactly where to insert something into this whole thing. And I'm going to keep everything ordered all the way along, right? And so this allows us to do some really cool things in terms of range, efficient range scans, the way that we actually insert things. More importantly, with the way that we actually automate the sharding of the database itself. Shards for us are ranges. And I'm going to show you how we do that too. I actually just cover this. So, so how do we take care of this, right? So each one of these tables is actually divided into oh my god, contiguous. Actually, this is 256 megabyte ranges. We've actually just upped this. We're getting a little bit more efficient in the way that we actually do these things, right? So every table is divided into these ranges. Think of ranges as a shard, but we have thousands of shards depending on the size of the table, right? Every 256 megabytes is a shard, is a range, right? These ranges, the size, the 256, we chose this because it allows us to do some really cool things around moving data around in a cluster and where things physically live, but also allows us to split things very quickly. I'm going to show you actually how that takes care of as well. Now, if you're going to do this, you actually have to have an index structure to understand where these things are located. So we create this. This is some special tables in Cockroach that are implemented within each range. And it's very much like a B tree, if you're familiar with that algorithm from computer science classes in university, right? So we're just implementing that. Now, it allows us to do some really cool things like imagine a range scan. I don't have to go find all the data and then scan. I know exactly where that data is going to be. So there's some kind of interesting things. But it allows us to do this automating of sharding the database itself. Now, I'm going to divorce the physical from the logical as we go through this, and I'll show you actually how data gets written to physical disks next. But for instance, I want to insert this record Sunny. I'm going to go through the B tree. I know that's in the third range, and I'm going to go insert that. It's going to say, hey, is there space available? The range says yes, great. Insert that, wonderful, beautiful, everything works, right? Okay, now I want to insert this next record, Rudy. Well, there's no room in the in, man. I can't get this in here. I'm at my limit. Now, what happens is we automate the split. What we've done is we've created a new record in the B tree. Actually, this should be a 4 here. Sorry, another typo. But we basically split that range in 2 and evened the amount of records that were in each one. Now I have room. I can insert that record and I can go on. Now that range itself, that's a shard. I've just automated the entire sharding process. Now, we don't do this in real time as you're writing. We'll let things go a little bit so that we actually don't affect performance of a particular query at any moment in time. We take a more intelligent approach to actually doing this, but logically, that's what's happening under the cover. So I've now basically sharded the table into 4 shards, and I've automated all of that. This is what allows Cockroach to do some really interesting things from a scale point of view. We can scale up and down too. And so this whole reverse process actually happens as well as we kind of clean up things, right? And so some really interesting things. Now, this layer is really what allowed me to actually understand lots of different stuff. Now, the second part of this, and actually before I go on to that, is there a maximum overall DB size for each table? We're running databases of all different size, and really it comes down to, physical distance and physical side of the servers that you're running on. We measure this really in terms of, vCPU, transaction, and database volume itself. Reach out to us. We'll give you more exact details around that. I don't have that in front of me. I don't want to misquote, but somebody had asked that question. So there's no there's no kind of physical limit on this. It can really go as far as we can. The limits that we've run into is the cost of us testing it in AWS or on GCP. The cost of the hardware to actually push where we want to go. We have run benchmarks like TPCC. I think we're upwards of 140,000 warehouses or 150,000 warehouses. There's a blog post on that in our last release. So it gives you a little bit of a sense of scale of how far, we're testing our database as well. So, okay, so RAFT. RAFT is a really cool concept. If you're not familiar with RAFT, go check it out. If you're going to be doing distributed systems, any sort of these distributed concepts, there's 2 algorithms. There's RAFT and there's Paxos. Both of them are kind of accomplishing some of the same things. I'm not going to get into a debate about RAFT versus Paxos, but what RAFT is a distributed consensus protocol. So I like to think about it as kind of the algorithm that allows us to do what we do, and it allows us to distribute data intelligently, and it allows us to gain consensus when things are trying to be made consistent across replicas. What it's ultimately doing is it's creating these things called replica sets. So remember before I had these ranges, these 4 ranges, when we physically write these ranges to disk, we're going to actually write them 3 times. And that 3 times, each one of those is the exact replica. The 3 of them together is a replica set. And RAFT basically manages these replica sets. Now, this is the blue range over here on the right. It's a RAFT group, right? And one of those copies, one of those replicas, is actually the leaseholder. And the leaseholder is kind of special because it basically coordinates and makes sure that all the data is correct across the 3 replicas. We use it as kind of this authoritative source, and it allows us to actually help control how we implement consistent transactions in the database itself, right? And so all of this is done. It ensures that there's atomic replication of commands. And so atomic means basically, did it commit or not? And it allows us to basically get quorum, right? So 2 of 3 of the replicas have to commit for us to actually commit a transaction, right? And that's we're going to ensure that the data is always correct. The leaseholder plays a very, very important role in this entire concept, right? So again, each range is a RAFT group. We default to 3. It's configurable. We see people go to 5 or 7. It really depends on kind of what you want to survive and some of the requirements of your particular application. But typically, in an implementation of Cockroach, there's tens or hundreds of thousands of ranges in a cluster. So imagine hundreds of thousands of these little shards and replicated across thousands, hundreds of nodes, right? And so it's pretty complex, and we've been working on this for actually in all time probably about 6.5 years. It's funny. One of our founders, Ben Darnell, who's probably in the top 5 in like software engineers I've ever met in my life, and I've had the pleasure of meeting some really, really interesting people. Ben's an amazing developer, and it's funny. I heard him say once, I can code RAFT in college in like a day or 2, but to do it in a production database has taken 5 years. And he's right, because there's a lot that can go wrong. And so at Cockroach, we've spent a lot of time building this, and it's the corner cases of a database that can actually cause issues. And so we feel we've worked out a lot of the kinks and are pretty far along in terms of maturing this database and gestating it to its full potential. And so this stuff while it seems pretty straightforward on paper, in reality, in production systems, lots of things can happen. And so we spent a lot of time building out this this distributed consensus in Cockroach, and it's a real key piece of the database, but actually really key to the architecture and understanding kind of how this works, right? All of these things work together. I talked about ranges and how we're able to split data, the KV. I talked about RAFT and distributed consensus. So let's see how this kind of all comes together to kind of help us understand, how we get scale, how we get resilience, how we can tie data to location, how can we implement, how can we guarantee this isn't eventually consistent, this isn't repeatable read, and this isn't a NoSQL database where it's kind of maybe the data is correct. No, we are guaranteeing data is correct, so that this is good enough for system of record financial transactions, right? So how do we pull these concepts together, the core of KV and RAFT together to deliver some of these things? And that's the next section of this. But you need to understand for me, it was critical to understanding those 2 pieces to help build on top of, right? And so let's go into that now. So where we place these replicas, remember the RAFT group, I have 3 versions of that same range. Where we place this basically depends on you and what you want to do with that data. And so when I think about it, it's like, remember this whole logical versus physical thing, it's really kind of up to what you want to do. And that's number 1. We also can actually control this based on, volume. And so we can just balance things. We can understand versus diversity, like what do you want to fail? Like what do you want to survive? We could actually do it via workload. There's lots of different things. Let's just walk through this. So here's my table. This first range, which has the dogs of Carl to Jack, they are going to be written to physical nodes. The physical nodes are represented as cylinders on the right-hand side. And what we're going to do is we're just basically going to start writing them. I'm going to write the second range to 3 different nodes. I'm going to write the third range to 3 different nodes. What we've done here is we've basically balanced the cluster so that the data, the amount of data, the volume of the size of the data is balanced across these 4 nodes. That's typically by default what we're doing, right? And so, but what you'll see is there's a copy of the data on each node so that if one node goes down, I'm going to survive that. I still have 2 copies. I still have this quorum, so I can still write, right? But we can also do things like, we use heuristics in the database itself to actually understand, if a range is being accessed more than another part of the table, we can actually allocate that to its own nodes in the cluster. So look at the blue range is having a high workload. We can actually, the database is actually smart enough to rebalance where data is so that we can meet the needs and SLAs of customers that are asking for that data. We can kind of segment it off so that we can actually meet load, right? So the data is available during the replication. The data is actually available as soon as it's written. Replication happens in real time. This whole automatic splitting of the data actually goes on in the background, but like once the database is there, once it's started, reads and writes are available all the time. There is no like moment in time where I'm rebalancing and all these different things. It's basically reads and writes are either going to be queued up or serviced immediately. So the data is there. Now, typically, depending on how you configure the database, from a P99 latency, there's lots of other webinars that we've done where we show how we can actually alter table in real time to actually, reduce latency. So you're getting a 3 millisecond, read no matter where you're at on a planet, right? And so there's lots of things that we can do, but we're doing that all in real time. And when we do alter table or we, upgrade a node or upgrade the entire database, we can do all of this with 0 downtime, which is pretty cool as well. So that was one of the questions that came in. The other cool part here is any node can accept a read or a write at any time. Remember that. So every node is a single consistent gateway to the entirety of the database. So the other thing we can do, using this overloading the key, we can actually overload the key with, say, a column. I could take the country code that for each particular dog, right? And I can embed that into the key now. And now all of the ranges that are this, oh gosh, I'm so colorblind. Blue and red, I can actually segment those to live in particular places. This is a little bit off. This should be orange and this should be red. Sorry about that. Man. But we can do this so that we can actually tie data to location, because now I want to make sure that dogs that are located in the EU are actually on nodes that are living in the EU, so that users in the EU are going to get low latency access to that. This also helps us do some really cool things and automate, the compliance with, some of these data these jurisdictional controls over data. Privacy laws like GDPR. We're not the solution for it. We absolutely can help though, with residency of where data is going to live. And it's a very unique concept in Cockroach. Again, we built it because of the latency thing, because ultimately, when you're doing distributed systems, your biggest enemy is the speed of light. And for us, how do you actually take care of that? Well, you put data close to people, and you work within the speed of light, right? So that's another cool way in which we can actually place data across a cluster, unique to us, and to me, pretty awesome, right? So we also can rebalance replicas. So when I add a new node, I'm going to spin up a new node. I'm going to point it at the cluster. I could do this on this laptop right here. And the cluster is smart enough to just rebalance everything. So here I introduced a new node. What it does is it basically says, let me just rebalance this so I'm good. So it takes one of the replicas here. But imagine there's hundreds of thousands of replicas going on. It would just rebalance things so that we have even consistency. It's kind of cool when you do this in the UI itself. It shows you how things are under replicated, or when they're balancing out. And you can see this across all the nodes. Oh, by the way, the same way in which every node can service a read or a write, Another really cool thing about Cockroach is every single node can deliver the DB console to you. So we have an admin UI that allows you to basically configure and look at things in the database. You can point that at any node, and you're going to get that you can see the DB console. So the entirety of the database is another kind of core distributed systems principle here. When you use distributed systems, having each kind of binary to be exactly the same is critical. And in Cockroach, we definitely maintain that as a key thing. Every node is the same exact binary. There's no two different types of nodes. They're all exactly the same. What's allow us to scale very, very easily, right? It's very simple and very straightforward. We can also survive a failure. I showed you that on the introduction slide. So when something goes down, what happens? These replica sets, the three replicas. Well, right now the red replica and the blue replica are like, wait a second, where's my third piece here? It's gone. Well, what's going on, right? Well, it's smart enough to actually understand that replica set is smart enough to understand, like, wait, if it's been more than like a minute or something, create a new copy of the third piece of me so that I can actually get quorum rights. Because in Cockroach, when you write to the database, I'm going to show you transactions as well. You have to write to 2 of 3 nodes. Quorum rights is critical. And so, okay, this is how we survive. The RAFT is smart enough to understand I'm missing something, so create a third copy. It does it. We can also survive these kind of temporary failures. Every once in a while, you'll lose connectivity to a node, and so you don't want to like hard reboot and recopy data and then rebalance all these things. So we can actually replay a little bit. So as long as 2 of 3 have written, these replica sets are smart enough to actually replay, small little, nits in time, so you can actually catch one of the replicas up, right? And so we'll do that as well, which is kind of cool. And it's really kind of how do we optimize for performance and whatnot, right? So, okay, so that's the core of how we distribute data and how we scale and how we actually do resilience. Let's talk about consistent transactions. Now, I'm going to go through a model here that allows you to think about how we implement this. But ultimately, at the top layer, I've said this before, we are implementing serializable isolation, which means basically we are guaranteeing that data is correct in this database. Now, how do you do that at scale? There is a lot of really cool software engineering that the team has done here to ensure that we are getting consistent transactions no matter where anybody is on the planet. Because remember, every node can service a read and a write, which is actually really, really important, right? So I'm going to go through the simplest explanation of how we actually implement transactions in the database. It's a little bit of the logical versus the physical here. Now, there's a lot of things that can go wrong. We have a lot of material that walks through this. The life of a transaction is a great part of our docs if you really want a really detailed understanding of what this is. And while I'm at it, I say this on basically every single webinar and every single Cockroach Hour I'm on is our docs are phenomenal. If you want to learn any of this stuff actually the right way, because the way I talk about it is I'm just a marketing guy. What Jesse and the team has done in our documentation is phenomenal. As an open source project, it's one of the things that I'm most proud of here at Cockroach Labs. And there is a section called the life of a transaction, which goes through this really wonderful, intricate detail of how this works. But I'm going to give you a high level understanding of how this works, right? So I have this transaction over on the right-hand side. I'm going to insert 2 values into the dogs table. Now, when you do that in a database, ultimately underneath, that query gets written up into 4 different steps, right? Of course, there is a begin transaction. I'm going to write Sunny, I'm going to write Aussie, and then I'm going to end that transaction and commit. Now, this gateway here that I'm pointing at, right? This thing is any node. Remember, any node can service this query. It could have come through node 1, node 2, node 3, node 4, any one of them. We're just generically saying it's gateway. It is the gateway node. Any node can service a read or write. Now, what it does is it says, okay, great, I would need to write Sunny. So the first thing I'm going to do is I'm going to find the RAFT leader that we talked about, right? I'm going to say, hey, look, I need to write this data in here. And it's going to say, great, hey, I've got room. Remember, I don't have to do this splitting thing. Hey, I've got room. Cool. Okay, let's insert Sunny. And what the RAFT leader does says, hey, replicas, my followers, can you actually write this thing? And they put a temporary hold and they say, okay, temporarily, yeah, I'm good. And so as soon as one of them comes back and says, okay, great, cool, I can now write, I can say, okay, we're good here. We can go ahead. Let's go ahead with the second step of this overall transaction. I haven't committed anything. These things are still yellow, which means they're kind of temporary holds on that data. because I can't commit this transaction until everything is committed. Now, the second part is it says, okay, great. Let's go now and write the second piece, this second Aussie record. Okay, great. As soon as one of those, as soon as I get 2 of 3 that are in this temporary kind of hold mode, I can now write an acknowledgement back to the original node saying, hey, I'm good. What happens is in this original transaction, it says, okay, great, I am now committed. And it communicates out to all the records to clean up. It says all the records say, okay, let's clean it all up. And everything gets committed. And I send an acknowledgement back to my original requesting application, and the database is good. Now, lots can go wrong here. One of the tricks to implementing Cockroach is, you have to put some retry logic, because if things fail, these are complicated things that are going on in the background. You actually want to do those sort of things. This is kind of a best practice. We can ease up on some of the requirements, especially around reads. I can actually do follower reads. There's lots of different things that we can do, but I just wanted to give you kind of the high level understanding of how transactions work in CockroachDB, right? Okay, great. Okay, there's been not a whole lot of questions, and that's cool. I hope this is valuable. A quick question, somebody asked me, why 2 of 3? Well, that's just quorum. If I had 5 replicas, I would need 3 of 5, because you just basically need the majority. And that's really what's going to give you quorum when you're writing, because now I'm guaranteed, because as long as your RAFT leader is correct, the RAFT leader is going to make sure everybody else in that RAFT group is good. Okay, so all right, great. I got a little feedback, very valuable so far. So thank you for the feedback. I hope this is good. It's going we're pretty good. I got 22 minutes. I think we're going to be pretty good here. So, okay, so distributed SQL execution. So what we're doing here is the KV layer allows us to read data from anywhere, right? And allows us to put things in the right places. But I can't abstract like network latencies out of that, right? And so that's kind of unique to us, right? What we do is we could push SQL execution down. So if you're familiar, I'm very familiar with the Hadoop thing. I worked at a company called Hortonworks a long time ago. And I'm pretty familiar with MapReduce and kind of how that works. If you think of kind of the core concepts in MapReduce, where we can actually push down execution, right, map, and then reduce back up at the top level, is kind of the similar kind of thing of what's going on here, right? We can decompose a query into pieces, push it down to where data resides, and then kind of pull things back up. And that's exactly what we're doing in Cockroach. Now, it's a lot more complicated than that. Any implementation of things like this, again, I'm just the marketing guy talking about it at a high level, but the core concepts are all there, right? And so here I want to count customers by country, right? And so what I'm going to do is I'm actually going to go ask one of the nodes, whatever's closest to me, right? And it's going to say, hey, listen, go do a scan. I'm going to do a scan in one region, scan in the next, scan in the third, right, from the customer table. And what it's going to do, it's going to then do that group by, so I can only start to do that count. And it's going to bring that all back to the original place, which is the original query. And I can actually send that back to the originating person, right? So what I've done is I basically just pushed down execution. Now, again, this is another area in distributed systems where the complexities here are tremendous. I mean, we're talking about years of work. I don't want to underestimate the amount of time and work it goes into actually making that happen. It's pretty complex and pretty awesome. Now, what's really cool is we've actually built out a cost-based optimizer. If you're familiar with the database, a CBO is kind of one of these advanced topics that DBAs use to basically really optimize how these things work. And this is a pretty good example of like, okay, where am I grouping? How am I grouping? Which order do these things happen in? We're actually using heuristics underneath the covers. And we have this really great cost-based optimizer. And cost-based optimizers are complex. We've added the complexity of where data lives into our cost-based optimizer. And so we're still building that thing out. I mean, there's lots of things that we can do in there, but man, there's some really, really great tech. Now, if you're interested in how we actually built a cost-based optimizer in Cockroach as a distributed system, we published a paper to Sigmod. It was about 4 or 5 months ago, led by one of our awesome engineers, Rebecca Taft, and team. And it really outlines, like, way better than I can ever talk, exactly how a lot of these concepts work, and outlines really kind of the stuff that we're doing in our CBO as well. So, okay, so great. Now, let's talk about latency. So if you're going to implement a database and you're going to be distributed, your ultimate competitor is the speed of light. Ultimately, I mean that really is that's the problem, because look, I can't beat between New York and Sydney, it's what 250, 300 milliseconds for light to travel from one place to the next. That's a challenge, right? Especially as you're trying to kind of, commit records. What happens if I'm going to execute a transaction in New York and I'm going to execute a transaction in Sydney, and I have two different nodes and it's one logical database and it's on the same account, and I can't have that conflict, right? So how do we actually deal with that in a distributed system? And there's some really cool things that we've done. But most importantly, how do we get these low latency access to users? And this is kind of one of those unique things about distributed database. Now, look, Cockroach is a wonderful database. It's really as simple as we are. I don't think I said this up front, but this is a SQL syntax, and we are wire compatible with Postgres. So this just appears to be like a Postgres database. And you know what? In a single data center, it's awesome. Like I can have 3 or 4 nodes, and I'm going to be guaranteeing that it's going to scale up. I just add more nodes. It's going to scale everything we just talked about. But also, you don't have to start thinking about these active passive systems, because we can get RTO, RPO down to 0. It's all active all the time. Now we do things, people ask us about backup and restore. We have those capabilities. It's in the core product, the free version of it. We provide it in Cockroach Cloud. But one of the things that we actually do is distributed backup and restore as well. Like, how do you actually know where data is, and you can't just back up to one location. That would cost crazy amounts of money from an egress point of view. And what about the data compliance? Shouldn't backups be in the location where they should be too, right? From a compliance regulation. So we do that sort of stuff too. These are all issues with the speed of light. And so the next section here is, let's talk a little bit about latency in Cockroach. So in the beginning, it was really simple, right? I had an app server and I had a database, and the speed of light was, it was, gigabit Ethernet, and that was pretty quick, right? But what happens in the cloud era, and as we get applications all over the place, well, it's 70 milliseconds round trip from the West Coast to Virginia, and it's probably about 12 from, where everybody's upset about the nor'easter coming up, in the Northeast up there against that database. It's pretty good. 70 milliseconds is pretty good. I think ultimately, there was a person at Google, Paul Bechtel, who said that I think, there's this thing called the 100 millisecond rule, where, 100 milliseconds is that time where humans feel things are real time. And so how do you guarantee transactions are going to be under 100 milliseconds? For us, we love to optimize down to the single millisecond range. And there's lots of things that we can do in our database to help people with this, right? But typically what happens when I have this implementation, I have this failover system too, where I have this active passive thing where, my active database is in Virginia, but then I have a failover full instance where I'm doing this async replication, so that in case something goes wrong, I could turn off and I can bring Arkansas online. So, but this 2 data center resilience thing is really, for us, we believe, something of the past. I mean, why not have everything active? This is super expensive. When things actually come back online between the secondary and the primary, how do you resolve these things? Lots of different kind of issues. The way we think about this is, how do we set it up so that we just have active everywhere, and we can survive failures across the board? And we can give low latency access to every single person in the country, right? So that, these round trip times between these various different places, we're getting down into, under 20 seconds or under 40 milliseconds, right? And so for us, the way that we think about this is actually, let's implement and think about the logical model, which is important, but this physical model of where data lives. What do I need to survive, and how fast do I need to get data to end users, right? And so that's kind of what we do. So now, for all writes over here, it's 12 plus 12. So the grace on 24, it's a 7 millisecond back and forth, and only 24 milliseconds for writes, right? And so we're actually able to locate data wherever it's going to be, and to provide really kind of a quality of latency across the board. Now think about this, just a North American or US centric point of view. Sorry for everybody else. But when we start to go across the whole planet, these things get really interesting. Now, how do we do this? It's actually pretty simple. Now, somebody was asking about Cassandra versus us. Like, we've actually built this into the DML, the DDL itself, like the way you actually configure the database itself, right? And so what we're doing is we're basically creating these partitions, right? So all of the values that are noted as US West actually get, written to the West partition. All the central are going to be written to the central node. So you look at these. This is US West 1, US West 2, Central 1, US West East, or US East, right? And so what we're doing is we're physically naming each of the physical locations, and everything that's in the West partition gets written into those things. So we can actually just, at the table level, control this. And so every row is going to be placed into the right place. We can also alter partitions in real time, so that, say I added a new node or I added a new region, we basically, it's just an alter table where we're just altering the table, and the database itself is going to rejigger where all the data lives, which is pretty awesome, right? So let's say I open up in Europe and I want to actually create a zone there. We just create, we do zone configurations, and all the data that was European, that was in these, whatever, how many nodes we had in North America in that example, would start being pushed over into the nodes that were in Europe, because that's where I want them to live. This is all tied back to that KV thing and how we actually overloaded that key with that country code. This all plays into that. For us, it's really simple, an alter command on the table. And in redoing the zone configuration, the database takes care of all this movement of data, so we can guarantee low latency access. Again, we've shown this in a couple of different webinars. If you haven't joined us before, my friend Keith has done this. My friend Chris Cassandra has done this. And we just do alter table commands. And you'll see the P99 latency go from 35 seconds down to 6 milliseconds, right? And so pretty awesome stuff. And so that's how we actually take care of those things. So let's just, okay, quick check time. So I'm not going to cover that. And then, so let's go finally into kind of some of the optimizations that we're doing under the covers. And this comes back to some really interesting software engineering that we've done that, I think, CockroachDB itself was really written with a lot of the same core principles that Google Cloud Spanner. The Google team actually unleashed the Spanner white paper to the world about, oh gosh, I don't know, 8, 9, 10 years ago. Gosh, I'd have to look it up. I'm sorry. And a lot of the core principles that were outlined in that paper are right. That is kind of what has to happen for a distributed database. We've been building for 6 years. Remember I said, like, a lot of corner cases, a lot of things. Well, there's a lot of corner cases around performance. And, like, I think about things that we've done around etcd and how we actually, multi-master etcd is a cool thing, but how do you do that at scale across the entire planet, right? And how do you avoid, split brain and these sort of things? We solve those issues. And, if you are interested in understanding how we've done these things, the engineering blog here at Cockroach, we divulge all these things. Again, that SIGMOD paper is a really good thing. But I want to go through kind of some performance optimizations that we've done for distributed transactions. This is truly for distributed transactions. And we're talking about not just in a single data center where latencies are kind of low, right? Because it's just across a couple of AZs, whatever. But like when you start going across a planet, there's some problems that arise, and timeouts actually happen because of these things. And I was talking about a transaction being written in Sydney and New York. How do you guarantee? How do you make sure that locks aren't too long? Somebody was asking about, how do you deal with that, right? And so it gets really, really difficult. I don't want to stall anything, right? And so typically there's kind of like some of the things that we've done. We've done like lazy and pipeline transactions. And so if you think about a query, right, here's the 3 steps again. So in serial, what you're doing is like, okay, great. I'm going to start this Carl transaction. It's pending. I write Carl. I come back. Great. It's going. Then I'm going to start writing Nigel. Nigel comes back. When both of these things happen, these keys are done. I commit and it comes back, right? So that was the total amount of time for that transaction. It's serial. I'm doing one after the other, right? What we're doing basically, understand, is we're actually writing Carl and Nigel at the same time. We're waiting for those things to come back, and we can then commit, right? So we've actually have this kind of, the difference here, the time difference here is significant, right? And so this is basically, we're pipelining things. Same thing that we've done in computer architectures, if you ever take that class a long time ago. So some really cool things here. What we've done is actually we've taken it to a wholly other level. And we've implemented and designed something called parallel commits. Now, if you're familiar with Jepsen and these sort of things, I know Kyle and team, they do some amazing things. And I think the very first time we actually implemented this and we put it out there, I believe is in our release last spring. Maybe it was 2019 in the fall. regardless, we introduced basically something called parallel commits, and I think to a lot of people it was like, oh my god, what did they do? Like it was this weird black, like some magic happened. And the way that I like to describe it is you can't really beat the speed of light, right? Like that's just impossible to do. That's just a number that's there. That's a primitive, right? So how do you get past that? And so what we've done, if we haven't changed the speed of light, but we've changed the photons, right? We changed what's being sent and what's coming back. And so how do we reduce latency to one round trip in all the common cases? And what we do in order to do that, you actually have to kind of clean up the transaction state after the fact, and you kind of have to do a complete transaction up front. This staging thing comes really interesting, and so this whole like description that I had before, where I was kind of step, that's all kind of happening in parallel in many of the ways, right? And so let me just show it in kind of the same way. So this was that transaction where I'm writing 2 records, and this is the total amount of time. Now we're taking what we've already done, the way we pipeline transactions, and we added parallel commits to it. And so what we're doing is we're saying, look at Nigel and Carl, when they actually get committed here, we're sending basically the transaction, the keys for Carl and Nigel in a staging mode, and these 2 transactions all at once. So basically kind of what we're doing is we're committing the transactions on one node or in one area, and we're saying, hey, look at, take that and the transaction and the picture around it, and say, send us all over. And on the other side, as long as that is kind of looking the same, like this is going to commit all this, the status, and we can actually just commit everything at once. And so we've replaced this kind of the commit marker with one that's distributed. Now that's a really complex topic and really difficult to do in under 2 or 3 minutes. And some pretty awesome software engineering. I'm gonna actually go check out the Sigmod paper where we get into it in that if you're really interested. Now, if you're a distributed systems person, I would go check this out. Now, if you're just a consumer of a database and you're understanding like why is this important, this is really what allows us to do some really cool things in terms of solving the latency problems at scale. This is one of those things, like just the same way that being able to tie data to a location is very special in Cockroach. This is one of those things that I feel is really, really special and kind of, look, I'm an ex-engineer. It's one of the things I'm really proud to work with this team because it's pretty cool stuff, right? And so go check it out. It's great stuff, and we have lots of stuff there too. This is all proved with TLA plus, and so people ask us, how does this actually work? So we've actually gotten times, way down, and that's just a really key piece to actually implementing a distributed database. So. All right, so we have covered all of these topics. That is a lot to do in an hour. There were a few questions. I did take them along the way. Somebody was actually asking about Kubernetes along the way. If I can find that question. What would be the best way to deploy and operate CockroachDB? Let's say would be a good idea to use from Kubernetes. Great question. We are actually a really good database for Kubernetes because we are a distributed system. We were built to be distributed and working within that architecture. We're just very well aligned with that. We've published an operator, so if you want to go check that out, our operator is available. The core kind of database though runs very naturally on top of stateful sets and naturally in pods. The whole way in which we survive failure lives the same way as like this ephemeral nature of pods in Kubernetes. So if you're familiar with that, like I said, I was at a company called CoreOS, and CoreOS did a lot of the early work in the Kubernetes community, and they were since bought by Red Hat, and that team still does some phenomenal things. And I remember our CEO at CoreOS is a guy named Alex Polvey, and Alex Polvey was on stage with Spencer Kimball, the CEO of Cockroach. Spencer is also a pretty awesome developer himself. And they were showing a database that they couldn't kill. They were just killing off pods across multiple different cloud providers. And this is at OpenStack Summit like 4 years ago. And that's this database. This database was architected for Kubernetes. So if you're looking to deploy an application in Kubernetes, my personal opinion, there's not a better database to use if you want to run it on Kubernetes. I leave it to you to try and play. We are happy to help you through these sort of things. We have Cockroach University, which, please go check it out. It's free. It's hands-on coursework. We're constantly adding new courses. We're going to add a Python course pretty soon. Actually, it's already there. There's a bunch of new stuff coming, but it's all free. And then, I would also implore you to, if you want to go and use Cockroach, there's CockroachDB Core, which is the open source version. CockroachDB Enterprise adds some things like some more advanced capabilities around CDC, advanced RBAC controls. There's just advanced enterprisey features. But Cockroach Cloud is a real simple way to go, and we'll give you a free cluster there as well. So go check that out if you want to start playing with it and start building apps against it. So. Okay, so I am at 3 minutes left. There were a couple questions here. What I'm going to do is, instead of packing this into the end, let's give you your 3 minutes so you can get to your next meeting on time. But I wanted to thank everybody for joining us today, and I hope this was valuable to you. Again, please do take the survey. We're trying to constantly make these sessions as useful as possible. There has been some really nice comments in the chat, like this was very valuable. Thank you. We do want to make this stuff valuable and useful, not just from a database point of view, but sharing these concepts around distributed systems. I think that is the future of what we're all doing here. I'm pretty excited about it, but I'm also really excited to work here at Cockroach Labs. I think, this is truly an evolution of the database, something that I believe is the future. I think I joke internally, I feel like we're living 3 years in the future sometimes. And there's some really cool stuff here. So again, thank you. Take the survey, visit our website, check out our docs, read our engineering blog, a lot more detail. The Sigmod white paper is awesome. Check out our blog for that. So thank you, everybody. We'll send a recording out to everybody and have a great day.